Okay, we're going to go over acids and bases. That's our next unit. So we'll start off with some definitions. First, acids. Acids produce hydrogen ions, which can be in the form of H plus ions or H3O plus ions, which is basically an H2O molecule, a water molecule with an extra hydrogen. Hydrogen ions are protons. Basically, they have lost the one electron, and so they are protons. We call H3O plus ions hydronium ions. Here are some examples of some acids. We have HCl, hydrochloric acid, HC2H3O2, acetic acid, and H3C6H5O7, citric acid. Hydrochloric acid found in your stomach, acetic acid vinegar also found in fruits and vegetables. Yeah, well, let's see. We'll start again, won't we? Yeah, you have something you can do. Okay. All right, we're going to cover acids and bases. First off, acids produce hydrogen ions, H plus, or hydronium ions, H3O plus. Basically, hydrogen ions are protons. They have lost their one electron. Or the hydronium ions, H3O plus, that's just a water molecule that has an extra hydrogen. In both cases, they are positive ions. We have some examples here of some acids. We have hydrochloric acid, HCl, found in your stomach. We have acetic acid, vinegar, found in fruits and vegetables, and of course, salad dressings. And citric acid, found in citrus fruits, lemons, limes, oranges, grapefruits, etc. Note, all of these acids, when you see their formula, they have a hydrogen in front. In fact, the number of hydrogens that they have in front will match the charge of the negative ion, the anion. So chloride ion, charge -1, we have 1 hydrogen, whereas the citrate ion has a -3 charge, we have 3 hydrogens in that case. So some examples of some acids. Properties of an acid. The word acid comes from the Latin word acidus, which means sour. Acids have a sour taste. Think, again, lemons and limes, for example. Acids and bases form ions, therefore they conduct electricity. Acids corrode metals, and when they do so, they produce hydrogen gas, H2 gas. Acids also corrode carbonates. The corrode means they eat up or destroy, disintegrate carbonates, limestone, marble, concrete, and in this case, they produce CO2 gas. In fact, we poured some acid just the other day out on the track on one of the cement concrete platforms used for the discus because it had gotten too smooth. And by pouring some acid on it, that will in fact eat away some of the concrete, make it a little bit rougher, not so slippery. Acids neutralize bases, and acids will change blue litmus paper to red. Now, while there is basically just one definition for acids, they produce hydrogen ions, we have two definitions for bases. The first one, that they produce hydroxide ions, that was the original definition for a base, sort of the opposite side of the acids. They produced hydroxide ions. This was called the Arrhenius definition when they were dissolved in water. Later on, however, they found that there were substances that acted as bases that didn't have a hydroxide ion, didn't have OH minus in it. And therefore, they had to expand the definition of bases. This is the Bronsted-Lowry definition. And so they determined anything that accepts a hydrogen ion would be called a base. So notice how the two kind of go together. Acids donate the hydrogen ions, bases receive or accept the hydrogen ions. Here we have some examples. Sodium hydroxide, NaOH, which breaks apart into a sodium ion and a hydroxide ion. These can be found in soaps. Magnesium hydroxide, MgOH2, which forms a magnesium ion and two hydroxide ions. These are often found in acids. Calcium hydroxide, CaOH2, again forming two hydroxide ions, part of lime, whitewash plaster. And then a couple of examples of bases that don't have OH in them. Baking soda, NaHCO3, and ammonia, NH3. So basically, anything that's got OH at the end, remember that hydrogen was at the beginning, here we have OHs at the end. Those are bases. And then we have a couple of special cases, the baking soda and the ammonia, which are also bases. When we get around to a quiz or a test on these, part of what you'll have to do is be able to look at the different substances and go, oh, these ones are the acids, or these ones are the bases. And as I said, acids are easy. They always got hydrogen in front. Many of the bases have OH at the back. Okay, some properties of bases. And if you do miss anything, it will be on the web page, so you can double check anything you might have missed there at the end, so don't worry. Properties of base. Bases come from the Arabic word al-qali. It sounds a little bit familiar. Remember our first two groups on the periodic table, the alkali metals, column 1, and the alkaline earth metals, column 2. And in fact, the alkaline earth metals were often first discovered because they were still left behind after a fire, and the ashes, bones found in the ashes, if the fire wasn't hot enough to burn up the bones as well. Bases have a bitter taste, so a little bit different from the acids. Sour for acids, bitter for bases. In fact, chocolate has a very bitter taste. If we didn't add a bunch of sugar to it, it would be really hard to eat. They feel slippery. So again, often find them in soaps and cleaning products. They corrode fats and oils and waxes. And again, think of using cleaning materials after you finish cooking and you've got maybe some fats or oils that have been splattered around that you need to clean up. And as I said, used in soaps and cleaners. They conduct electricity as well as the acids do, because again, we form ions when they are dissolved in water. They neutralize the acids and turn red litmus paper to blue. Sort of two sides of things. Neutral being in the middle, acids on one side, which do corrode certain types of things. Bases on the other side, which also can corrode other types of things. And honestly, you can be burnt by bases just as easily as you can by acids. They're just different extremes, different sides of things, but they are extremes. We like things neutral. We like things in the middle. Okay, basically, as you can kind of see, these go together. We tend to always find things in pairs. And so we have what are the Lewis acid-base conjugate pairs. And basically, the idea is if something is donating a hydrogen, therefore an acid, something else has to be receiving the hydrogen, and therefore you have a base. And so there's always two substances related by the loss or gain of that hydrogen ion. So in the example that we have here, we have nitric acid, HNO3, dissolved in water. Well, the nitric acid loses that hydrogen. It's an acid. And on the other side of the equation, we have the H3O plus. So the water molecule gained that hydrogen ion. And so we've got the HNO3 as the acid and the NO3 minus as its conjugate base. Now, why is the NO3 minus called a base? Well, if we were to go backwards, in other words, instead of from left to right, go the other direction, the NO3 minus would be gaining that hydrogen to come back and reform the HNO3. And so you've always got something that loses it on one side, and then on the other side would gain it back if you were to reverse the reaction. Likewise, the H2O was the base in this case. It accepted the hydrogen ion to become the H3O plus. If I go backwards, the H3O plus, the ammonium ion, would lose that hydrogen. Anytime you lose the hydrogen or donate the hydrogen, you're considered the acid. So always in pairs. So anytime you see in a hydrogen, you have to figure that's part of a pair. We've got an acid and a base. Something donated, something accepted what we were doing. Okay, salts, the third main substance of this topic. Basically, it's an ionic compound, so anything that's metal and non-metal put together. Salts are formed in the reaction between acids and bases. So basically, if we mix an acid and a base together, it's going to make a salt and water. So note the examples here. Hydrochloric acid and sodium hydroxide to make NaCl, table salt, and water. HCl and KOH to make KCl and H2O. KCl, potassium chloride, is a salt substitute, by the way, for people who can't have too much sodium in their diet. And then the third case here, we have phosphoric acid, H3PO4, plus calcium hydroxide, which forms the salt, calcium phosphate, and again, plus water. Notice that in every case, we form water and some kind of salt, not necessarily table salt. Again, any ionic compound, any compound with a metal and a nonmetal, or metals and nonmetals, is a salt. And so you can have different kinds of salts. But you got to be careful. You don't want to say this is salt water, because generally when people say salt water, they're thinking of like seawater. Seawater has a lot of different salts in it, not just one salt. The idea here is one particular salt will be formed and water. And so that's the way to think about it. And again, you're going to have to be able to distinguish between, hey, this is an acid, that's a base, and here's a salt. All right, how do we measure acids and bases? Well, we use a pH scale. Basically, it goes from 0 to 14, and it's used to measure the strength of acids and bases. In fact, pH stands for the power of hydrogen, and later on we'll look at something called pOH, which is basically the power of the hydroxide. It's just looking at how strong the base is, if you will, instead of how strong the acid is. pH is based on concentration. Notice the little H plus in the brackets, and then next to it you have 10 to the minus 7 M. That M is for molarity, moles per liter. And so we have a concentration. And basically pH is a measure of how concentrated the number of hydrogen ions is in the solution. The more hydrogen ions we have, the stronger the acid it is. Neutral would be right in the middle, a 7. Anything that is less than 7, we would call an acid. Anything that is more than 7, pH-wise, we would call a base. And then we break it into some kind of categories. Strong acids, the lowest numbers, 0, 1, 2, 3. Weak acids, 4, 5, 6. Weak bases, 8, 9, 10, 11. Strong bases, 11 to 14. Now, it's been simplified here with the whole numbers, but you don't have to have whole numbers. You can have things that are in between. So for instance, if I said something had a pH of 6.5, that would still be in the weak acid range because it is a little bit less than 7, but it's not very much less, so it's a weak acid. We also have some examples here of everyday substances that would fall into these categories. So lemon juice, a very concentrated lemon juice, not lemonade that you would drink, but lemon juice. Also think some of those jalapeno peppers or some of the other peppers that could burn your mouth. Those are the ones that would be strong acids. Weak acids, vinegar, milk, those are weak ones. Soda, generally speaking, is a fairly weak acid, but it's almost borderline to the strong one. Give soda a chance, it can corrode things after a while. Neutral, pure water, nothing in it. And then the bases, milk of magnesia, Pepto-Bismol, weak bases, NaHCO3, again, that's baking soda. That would be a weak base. And then the strong bases like ammonia, bleach, those would be strong bases. And again, this is a logarithmic type scale. So notice that we're matching the exponent of the concentration to its pH value. So a 10 to the minus 9 in concentration would be a pH of 9. We'll talk more about that in just a minute. We got one slide left and then we'll be done for today. And it's short. So the pH scale. Okay, last slide for today. Couple of words. Neutralization, adding an acid to a base or a base to an acid to produce salt and water. And then a buffer. Basically, a buffer is any substance that resists changes to pH and is generally made up of an acid and a base. We have buffers in our body to keep our pH in a very narrow range. Okay, well, we may eat something that's a little acidic or a little basic, and that buffer counters whatever we eat so that the pH in our stomachs doesn't get out of whack. And in fact, when it does, people have stomach problems. So buffers are designed to try to counteract that. Sometimes medicines will have buffers attached to them so that they won't be as upsetting to our stomachs. So that's the purpose of a buffer. We will do some more vocabulary later on, but these are the big two that we're going to consider. Okay, that's it.